Hi, in this podcast we'll start introducing the idea of using quantum mechanics in order to explain the structure of molecules, and in the process we will introduce certain concepts such as that of molecular orbital, which are very important, for example in your study of inorganic chemistry. So let's start from a relatively simple system, which is the hydrogen molecule, H2. So we've got two hydrogen atoms, so we've got two nuclei, one that we indicate here with the letter A, and one that we indicate with the letter B, and we've got two electrons, one indicated with number 1 and the second one here with number 2. So we've got a certain internuclear distance, which is represented by capital letter R here, and then we've got the distance of the first electron, one from nucleus A, R1A, then we've got R1B, which represents the distance of electron 1 from nucleus B. Same thing for the second electron, and then we've got also this distance R12, which represents the distance between the two electrons. Now if we were to try and write the Hamiltonian for this sort of system, then we will have all these terms that would have to be included in the Hamiltonian. So we've got the kinetic energy of the nuclei, represented by this term here. Then we've got the kinetic energy of the electrons, and as I said, there are two nuclei and there are two electrons in this system. Then we've got the potential energy of the internuclear repulsions. So we've got two nuclei, they are both positively charged, so there will be a certain electrostatic repulsion between those. Then we've got the potential energy representing the interaction, the electrostatic interaction between nucleus, each of the nucleus and each of the electrons. And this is obviously an attractive sort of term here. And then we've got the electrostatic repulsion between the two electrons. So as you can see, there are several terms, and because we've got two nuclei and two electrons, each of them will have three Cartesian coordinates describing their position in space. So in total, our solution to the Schrödinger equation is a function of 12 variables with this very complex Hamiltonian describing it. However, we can start introducing certain simplification to this Hamiltonian. So first and foremost, we can apply the Born-Oppenheimer approximation. So basically, since nuclei are much heavier than electrons, the electrons will be moving much faster than nuclei. A consequence of this is that we can regard the nuclei as fixed while the electrons carry out their motion. So what happens is that at this point, if we apply this approximation and we consider this approximation to be valid, then we can actually study electronic and nuclear motions separately. And in reality, we have already developed in our previous study of quantum mechanics certain models that can be used to simulate nuclear sort of motion. So for example, we've got the particle in a box, we've got the three-dimensional rigid rotor, we've got the harmonic oscillator, and all of these sort of models can be used to study nuclear motion. In this lecture we will be focusing on the motion of the electrons only. So let's see how we can actually do this. So we can assume a fixed configuration of the nuclei. So we can assume that there is a certain distance between the two nuclei, and we keep that fixed. And then we can solve an electronic Schrödinger equation to find the molecular electronic energy and wave function. So we can solve the Schrödinger equation just for the motion of the electrons, and this will give us a certain value of energy and a certain wave function describing that system. Then we can actually repeat the same process for many different values of the nuclear configurations, for many different fixed nuclear configurations. So we can move the distance further apart or closer together and start analyzing what sort of results we get in terms of electronic energy and wave function. And therefore we can actually find a picture that will describe how the electronic energy varies as a function of the position of the two nuclei. And you can see that the picture you will get is something that looks like this. This is a molecular potential energy. So we will have a certain distance, RE, where the potential energy of that system reaches its minimum. And this is what we call the bond length. So the nuclear separation when the potential energy is at its minimum is called the bond length. This term here, indicated with the letter D with the subscript E, is actually the dissociation energy. So this is the energy that we need to take the two atoms from their bond length distance to an infinite distance apart from each other. Okay, so this is called the dissociation energy. As you can see here, we've got also another term which is called the D naught, well, it's indicated with D naught in this particular graph, and this is because we should be familiar with the idea of the 0-point energy. So if we were to take into account nuclear motion as well as electronic motion, then we know that there will be a difference between the dissociation energy, which is this value here found at the minimum of the potential energy, and the energy of the system in its ground state, because we know that we've got this vibrational 0-point energy in the ground state, which is indicated by that D naught there. Now, this is all good, but we want to try and apply this sort of idea from this sort of qualitative point of view that we've just described. From a qualitative point of view, we want to try and apply them quantitatively to one of our molecules. But instead of starting directly with the hydrogen molecule, which has 2 electrons, we'll simplify our calculations a little bit, and we introduce the hydrogen molecule ion, which is basically H2+. So basically we've got a system that's made up of 2 protons and 1 electron. So here, this is the situation from a schematic point of view that we're trying to describe. So we've got nucleus A, nucleus B, a certain distance r between these 2 nuclei, these 2 protons in this case, and then we've got 1 single electron, a distance Ra from the first nucleus, from the first proton, and then a certain the same electron, a certain distance Rb from nucleus B, from proton B. So how can we describe the motion of these electrons, which will be somewhere in between these 2 nuclei? Well, we can use so-called molecular orbital theory. So basically the behavior of these electrons in this molecule will be described by a molecular orbital wave function, which will define the distribution of a single electron over the entire molecule. So that electron does not belong to proton A or proton B, so it does not belong to either of the 2 nuclei of that molecule, but it will be in a molecular orbital over the entire molecule. And molecular orbitals can actually be built using a linear combination of atomic orbitals. Okay, and this is indicated by this acronym that you see in this slide. So we've got 2 atomic orbitals, one that describe the motion of the electron in an atomic orbital around nucleus A, and one that describe the movement of the electron around an atomic orbital around nucleus B. And we can actually create a linear combination of these 2 atomic orbitals, represented by these 2 wave functions psi A and psi B, and this will be representative of our molecular orbital. So this is the wave function that describes our molecular orbital. And we've got 2 different ways in which we can actually do this combination. We can do it with a plus sign or with a minus sign, and N is a normalization factor. In this case, the two atomic orbitals for A and B are the same, and therefore there is only one normalization factor necessary for this linear combination. We know enough now about quantum mechanics that instead of calling this a linear combination of atomic orbitals, we could actually call it also a superposition of states. So what will this linear combination of atomic orbital look like? Let's first of all try and draw the two atomic orbitals separately. So we've got, this is position of electron 1, and this is the position of electron 2, and we know that the atomic orbital for the first electron, for the first atomic orbital around nucleus A will look something like this, and because this is symmetric with the position of the nucleus, we will have also this sort of distribution. Now for the second sort of atomic orbital, we will have a situation like so, which is basically the same, but for the other atomic orbital B. Okay, so this is A, and this is B. Now you can see we've got these two wave functions describing the radial distribution of around those two nuclei A and B. Okay, now what happens when we try and calculate the linear combination? We've got two identical wave functions, okay, around each of the atomic orbitals, but what could happen is that if we've got the plus sign between these two identical wave functions, in this region where the two wave functions actually overlap, there will be a constructive interference. So these two bits will actually overlap, and you will end up with a situation similar to that shown in this graph. So you will have a region in between where the actual probability of finding the electron will actually be larger than in the case of the two separate atomic orbitals. What happens in the case of subtracting psi B from psi A? Well, then you will end up with destructive interference. So this sort of situation depicted here. So in the case, let's remind ourselves that the probability density is given by psi times its complex conjugate. So in the case of the two separate sort of atoms, the probability will be density will be simply given by psi A squared plus psi B squared. So the two probability density basically for the two separate atoms added up. But what happens in the case of the linear combination? The probability density will be given by the same term psi A squared and the same term psi B squared. But we will also have another term which is the result of the fact that we've got a linear combination between these two functions, and that could have a sign plus or a sign minus depending on whether we are adding up the two atomic orbitals or we are subtracting them, and the result will be 2 times psi A psi B. So the idea of having these extra term here will result in a situation where the probability density between the two orbitals will be higher than in the case of the two atoms separately, or lower than in the case of the two separate atoms. So in the case of the plus sign in the linear combination, so we've got the psi plus function, which is made up of the sum of psi A and psi B being the two individual atomic orbitals. Then we've got an overlapping density in the middle and a constructive interference. So that means that the electron density is concentrated between the two nuclei. And this is a so-called bonding molecular orbital. So the energy of the entire molecule is actually lower than the energy of the individual atoms. Okay, so if we go back to the previous slide, we can see this is a situation where we've got this overlap in the wave function, which create this situation here in the probability density, where you've got a higher density of finding the electron in between the two atoms than you have in the case of the two separate atoms. And the result of that is that the energy of the molecule is lower, and this is a so-called bonding molecular orbital. This volume in which there is this overlap between the two wave function with a constructive sort of interference creates this sort of cylindrical symmetry along the axis that joins the two nuclei, the two protons in this case. And when you've got this cylindrical symmetry of this molecular orbital, we call this sort of orbital sigma. So the molecular orbital sigma plus wave function is also symmetrical to inversion around the center of the molecule. You can see it in the previous graph. So if we were to swap the two atoms around the center of the molecule, the wave function will look exactly the same as it did in its original position. So it is symmetrical, and we indicate these with a letter G, which stands for gerade, which is a German word for even. Okay, so basically what we have just described is this molecular orbital, which we indicate with the 1s, because it's made up of two 1s atomic orbital, sigma, because it has this cylindrical symmetry along the internuclear axis, and gerade, G, which represents the fact that it's symmetrical to an inversion around the center of the molecule. Now, what happens in the case of the subtraction between the two atomic orbitals in the linear combination? Well, in this case, you can see that we've got this sort of situation here, represented by this wave function here, and we've got a node in the middle, right in the center of the molecule, where the probability density of finding the electron is actually 0. So we've got a node where we have no chance of finding the electron. So let's go back to that slide. So we've got this destructive interference between the two atomic orbital wave functions that create this sort of effect where the wave functions in the middle cancel each other out. So this results in the electronic density being 0 in between the two nuclei. And this is called anti-bonding molecular orbital. So the energy of this molecule is actually higher than that of the individual atoms. So we still have got the same sort of cylindrical symmetry along the internuclear axis. So again, this is a sigma orbital. This should actually be a minus sign. So the molecular orbital psi minus wave function is antisymmetrical to an inversion around the center of the molecule, and we've seen that in the graph here. We can see that this is actually antisymmetrical. So if I swap them around, I obtain the same wave function I started from, but with a minus sign. Okay, so we call that ungerade, so we indicate that with the letter U. So in this case we've got a molecular orbital which is 1s, because again it's formed by 1s atomic orbitals. It's still sigma, because it's still cylindrically symmetrical with respect to the internuclear axis. In this case, we indicated with a star, which represents the fact that this is actually an anti-bonding molecular orbital, and then it's actually antisymmetrical to an inversion around the center of the molecule, so ungerade. And what these orbitals look like? Well, they look something like this. So here we've got the two individual atoms with their 1s orbitals. Then here we've got the constructive interference in the linear combination with the plus sign, and we've got this 1s sigma gerade molecular orbital, and here we've got the linear combination with the minus sign, which will create this destructive interference, where we've got this anti-bonding molecular orbital here, which is actually antisymmetrical with respect to an inversion around the center of the molecule. And this is shown here in the fact that you've got one part of the molecule where the molecular orbital wave function is positive, and one part of the molecule where the molecular wave function is actually negative. So what does the electronic energy look like in the case of the two orbitals? So let's start with the bonding molecular orbital, the one that we obtain with a positive sign in the linear combination, and you can see here that we've got a bound state. So we've got a state that has got a minimum of potential energy for the bonding orbital, and this is the one that will stabilize the molecule, and that is the sort of distance where you will find the two atoms. But in the case of the antibonding molecular orbital, the energy, electronic energy, is showing no minimum. So this is always positive and it has no minimum value. This means that basically the electronic energy in the antibonding molecular orbital of this H2 plus molecule is actually always trying to push the two atoms, the two nuclei, apart. So this creates some sort of unstable conditions. It's important to point out that in this case, basically in the case of the antibonding molecular orbital, the molecule is less stable than the two atoms apart. Another thing that's important to point out is to go with Atkins' words, is that the antibonding orbital is more antibonding than the bonding orbital is bonding. And this seems like a strange way of saying things, but the idea is that when you've got an antibonding orbital and a bonding orbital, you will have certain situations arising depending on how many electrons you've got in these orbitals and so on. We'll see an example of these later on. But this is basically due to the fact that we've got nuclear repulsion, which is common to both bonding and antibonding orbitals. So when you've got an antibonding orbital, this is more antibonding than the bonding orbital is bonding. So if I was to try and represent these on a certain energy axis, so let's say that we've got energy going along that axis there, and here I've got one of the 1s orbital, here I've got another one of the 1s orbital. If I was to place the two molecular orbital on these axes for energy here, I would have the antibonding orbital here, 1s sigma star, so this is the antibonding orbital, and this is the bonding orbital, 1s sigma, and this distance here is slightly less than the distance between the energy difference between the state of the two separate atoms and the antibonding orbital. So that energy is slightly lower. This energy here is slightly larger than this energy here. And this is what this sentence actually means.